Good morning. We're doing discrete structures. This is the discrete structures class. We're doing section 3.2 of the Ross and Wright book, which is about digraphs and graphs. Okay, so let's just tell you what digraphs and graphs are. They are, well, let's just tell you what a directed graph is. There are a bunch of nodes and a bunch of arrows in between those nodes. Okay, you've all seen them, you've all heard them. In the beginning of the chapter, they give you a lot of examples of such things. Computer networks are examples. Subway maps are a nice example of graphs. The nodes are the stations, and the maps and the arrows are the train going from one to the other. This is a weighted graph, which tells you distances. This is a tree. A tree is a form of a graph. Okay. This is some type of network with numbers on it. This is a flowchart. Flowcharts are forms of graphs. Okay, so there's lots of different examples of graphs. They show up all over. Okay, great. Let me just go through what a digraph is. We'll first do digraphs, then we'll do graphs. A digraph is a directed graph. We shorten that word to a digraph. G consists of two sets: vertices of G, and E of G, edges of G. Okay, together with gamma. Gamma is a function from E of G to vertices cross vertices. Now that looks totally abstract. I could have just written, I said it before. A graph is a bunch of dots and a bunch of arrows. But so the bunch of dots is vertices. Vertices is another way of saying dots. Arrows is edges. Okay? But it's written like this. So you have two sets and a function which takes an edge and goes like that. Okay, so I just want to explain this part. By the way, that's the end of the definition. But I'll show you in a second why this is the right definition. Okay? Because it goes as follows. The way to think of it is as follows. You have E is a member of edge of G. Okay? So that's E. Now, gamma, that's a Greek letter gamma. Gamma of E is a member of vertices of G cross vertices of G. That's what it does. It takes an input, an edge, and it outputs a pair. Okay? We're going to write this as follows. Okay? Gamma of E is equal to P comma Q. Okay? That is a vertex, a point, a node, call it what you like, and Q a node. Okay? We're going to describe that with the following beautiful, beautiful picture. And the following beautiful picture goes as follows. You have a node P, you have a node Q, and you have an arrow E from P to Q. Okay? So the E is a node, we call it E. I'm sorry, E is an edge, okay, or an arrow, okay, and this describes where it starts and where it ends. So P is where it starts and Q is where it ends. So let's go through this again. There's a function that takes every single arrow to starting places and finishing places. That's it. Okay. Now, this is the right definition. I'd like to show you why this is the right definition by giving you an example of a graph. Okay, so I'm going to give you an example of a graph given as such, and then you're going to draw the graph. Okay, and you're going to see what I mean in a second. So here's the vertices. So here's an example of a graph. Okay, the vertices of G is equal to A, B, C, D, E. Can't think of a better list. Okay, and the edges of G are U, V, W, X, Y, and Z. Okay, and now I got to tell you how the edges map to the vertices. So we're going to do as follows. the edge and the gamma of the edge. So this is the function. Okay, I'm going to give you an edge over here. I'm going to tell you what the gamma is of that edge. Okay, and it goes as follows: U, V, W, X, Y, and Z. Okay, so let me tell you, U goes from A to C. Okay, V goes from B to E. W goes from C to A. I'm making this up as I go along. Okay, X goes from D to D. Y goes from D to A. And Z goes from E to C. Okay, great. Now, this is the right definition of a graph. It's two sets and a function which you can describe like this. Let me explain to you why it's the right definition of a graph. Because I'm going to do is I'm going to stop right here. I'm going to stop the computer and I'm going to ask you to stop your computer. Press pause, and I want you to draw a picture of this graph here. Okay? And I'm going to draw a picture of this graph here also. But I want you to do yours, and I want you to compare your picture to my picture. Okay? So we're going to stop here. You're going to take a piece of paper and draw this picture right over here. And then I'm going to draw my picture right over there, and we're going to see if who's correct. And you can see that that word doesn't make sense. Okay, I hope you wrote it up. Here's my answer. Okay, let's just go through it. You have edge U, V, W, X, Y, Z. You have vertices A, B, C, D, A, B, C, D, E. Okay, and that's the way I drew it out. Let's just do it. U goes from A to C. V goes from B to E, etc., etc. So that's the way to do it. Now, if you actually did this, you would get something totally different than that. Okay, you'd have something mixed up. You'd have maybe you'd have A over here, B over here, C over there, D over there. I don't know. You must have drawn it differently than I did. Now, question: who's right? Answer: it doesn't matter who's right. The point that's important about a graph is the connectivity, not the way it's drawn. Okay? How is it connected? How are they connected with each other? Not the way it's drawn. Okay? So that's the point. That's the proper way of storing it. The proper way of storing it is as two sets and then a function. Okay? Not with a picture. And of course, a computer you can't draw pictures anyways. So that's the main point here, is that we're not dealing with the picture, it's the relationship that's important. Okay, so the rest of the chapter is a few nice definitions. I want to just move this a little bit like this so that we can get both. I write with my left hand, so I want to be able to do this. Great. Okay, next. Okay. If you have a point P, and you have a point Q, and you have an edge, we'll call it X, and an edge, we'll call it Y, something like this, this is called parallel edges. Parallel edges. Okay. Two things pointing from the same place to the same place is parallel edges. You can have 3 or 4 or 5, or well, if you only have one, then there are no parallel edges. Okay? No parallel edges is the same thing as saying that gamma, remember gamma? Gamma is the function from the edges to pairs of points, is not 1 to 1. Let's just see what that means. Okay, this has parallel edges, so you have two different edges x and y, and they go to gamma takes them from P to Q. Okay, so no parallel edges means gamma is not 1 to 1. I'm sorry, gamma is 1 to 1. Gamma is 1 to 1 means no parallel edges means there's only one thing. So they wouldn't have two things going to the same start point and finish point. So no parallel edges means gamma is 1 to 1. Okay, great. Next, another definition. Definition, a path in a digraph, okay, is, so we're defining what the word path is a sequence of edges. Such that the terminal vertex of one edge is the initial vertex of the next edge. I'll show you what I mean by that. Okay, so we don't need this anymore. What I mean by that is a path in a digraph is a sequence. Well, you know what a path in a digraph is. You just start at some place and you follow the edges. Without picking up your finger, you follow the edges. But let's be formal about it. Okay? And so it says as follows. A path is a sequence, E1, E2, E3, En, okay, such that, let's just go through this. E1 goes from x1, that's a vertex, to x2. E2 is going to go from x2 to x3. Okay, you may as well put them in as ordered pairs. E3 is going to go from x3 to x4. En is going to go from xn to xn plus 1. Okay, so let's read it. A path in a digraph is a sequence of edges. A sequence is just a linear of things like that, such that the terminal vertex of one edge, the end of this thing, is the initial vertex of the next edge. x2, x2. This is the terminal edge of the terminal vertex of E1. This is the initial vertex of E2. This is the terminal vertex of E2, the initial vertex of E3. And so you have that. Okay? So, but you know what a path is. Okay? It's just you're going along. Great. More definitions. Definition. Okay. A path is closed. So now we're defining a special property of paths. So we have properties. A path is closed if the terminal vertex of En is the same as the initial vertex of E1. Okay, so it's closed. That means you start and finish at the same place. That's exactly what it means. So you start someplace, you go here, 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 and then you finish in exactly the same place where you started. Another way of saying it is you have E1, E2, E3, En, and such that this goes x1, x2, and this one goes xn to xn plus 1. Instead of having xn plus 1, it's x1. You go back to the original place. Okay? So that's called a closed path. Okay, great. Now let's do this. Now we're going to talk about a special type of closed path. So let's just review what we just had. We talked about paths, and then we had special types of paths called closed paths. And now we're going to talk about a special type of closed path called a cycle. Okay, definition. A closed path, x1, x2, x3, x4, these are the vertices it goes to, xn, x1. So this is a closed path because it starts at x1 and it finishes at x1, okay, is called a cycle if x1, x2, x3, all the way till xn are distinct. Means not the same. Okay, not the same. So here's a typical example of a graph. Okay. I left out the vertices because they're not that important. Okay, but if I start here and then I go here and then I go here and then I go back and even, well, I'm not allowed to do that, but I go here. Notice they met twice over there. Okay, they met twice over there. Forget that green line. They met twice over there. That's not a cycle. Okay, a cycle means something like this. Whoops, not allowed. Okay, you start here and you finish there, but there's no interaction. Okay, you don't hit any vertex. You don't hit any vertex twice. Okay, so that's called a cycle. So that's a special type of things. Okay. Okay, great. So these are relations. It's very nice. Why did we bring in graphs? We were talking about relations. Why did we bring in graphs? And the answer is because at the end of last section, at the end of section 3.1, we saw, at the end of section 3.1, we saw given a relation on a finite set, you can make a graph out of it. Well, guess what? You can go the other way around. Okay, so let's write this out. At end of section 3.1, we did the following. You had a relation on a finite set, and you made a graph out of it. Okay, guess what? I want to go the other way now. Okay, you give me a graph, and I'm going to show you a relation. Okay, so it goes as follows. It's a theorem, I guess. Every digraph, okay, still keep up at directed, so this was actually a digraph, but every digraph G, what's a digraph? A digraph is vertices of G, comma, edges of G, comma, gamma, okay, determines a relation. Oops. On V of G. Okay, so I'd like to show you how that works, and it goes as follows. So you just need an example and you'll see it makes total sense. Okay. So we're going to call this A, B, This is C. This is D. This is E. Okay, let's go through this. This has like this. This is like this. B goes to C. C goes to A. D goes to E. D goes to C. Okay, that pretty much takes care of it. Okay, so now that's a nice digraph. And now what I'm going to do over here is make a relation on that. Okay, so we're going to have R, a relation. It says a relation on V of G. So R is a subset of, we're going to call this digraph G. Okay, so we're going to call this subset graph RG, which is a subset of the vertices across the vertices. Okay, and basically it goes as follows. I'll tell you what R of G is. R of G is equal to, it's a subset of pairs, so I'll tell you what the pairs are. There's a pair for, there's an element from B to A. There's an element from B to C. There's an element from C to A. There's an element from D to E. There's an element from E to E. That's that. What did I miss? Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. This is the problem of not having a class behind you. D to E. Okay, and the only thing is D to C. Okay. So now, what we call this has a name. This is called the adjacency relation of G. Okay, and basically, let's just write it out this way. X comma Y is member of R of G. It's related if there is an arrow edge from X to Y. Okay, this is when they're related. Okay, so that's nice. Okay, good. I just want to say, okay, that takes care of the adjacency relationship. In the homework, so we're going to see something else called a reachability relation. Okay, but you're going to read that in the book. And basically, two things are related, reachability related, not if there's an edge between them. So we'll call this A, B, C, D, E, F, G, H. Two things are reachability relation, not if there's a single edge, but if there's an entire path. So A is related to D because there's a path from there. B is related to E because there's an edge, so there's a path of length 1. C is related to D, but C is not related to F because there's no path from C to F. E is not related to G or H or F. Okay, so we're going to deal with reachability versus adjacency. Adjacency means next to. Reachability means can you make an entire path to do that? Okay, great. Okay, now there's a few more definitions in the book, okay, but I just want to talk about what happens when there's parallel edges. Let's say you have A and B, and you have two parallel edges, X and Y. Okay, well, in the adjacency relation, it's going to look like this, A comma B and A comma B. Well, 1 second, that's a set. We don't care about repetition in a set. This is equal to A comma B. Okay, so the parallel edges don't really play a role here. So we're not going to be very much interested in parallel edges. Great. This is definition of a directed graph because we talked about things like this. Now we're going to talk about just a graph, which is about things like this, with no directions. Okay, so first we need an exact definition. So let's do that. Definition. A graph, not a directed graph, a graph, G, consists of two sets, just like before, nothing different. Vertices of G and edges of G. Okay, we know V of G is vertices, E of G is edges, and a function gamma, just like before. Gamma goes from E of G. Okay. Now, let's just remember what happened before. Before, it went to V of G, don't write this, cross V of G. Okay? But now we don't want that. Now we don't want that. We don't want a starting place and a finishing place. When we were dealing with a direction, we had a starting place, we had a finishing place. But here, what's the starting place, what's the finishing place? We don't have them. We don't have where it begins and where it ends. We just have, we don't have a where it begins and where it ends. We just have, it goes between 2 points. And so we don't have a starting place, an ordered pair. We don't have an ordered pair. When we said this was an ordered pair of elements, we don't have an ordered pair of elements. Instead, what we have is as follows. E of G grows to, don't move, goes to the set of not ordered pairs, but set pairs, U comma V, such that U comma V is a member of vertices of G. Okay, so we write that. We'll say, let's say you have, let's do it clearly. Let's say you have E is a member of edges of G, and let's say I say gamma of E is equal to the set T comma U. Okay, what that means is that there's a point called T and there's a point called U, and E goes from one to the other. I'm not saying who's the beginning, I'm not saying who's the end. The main point is, with directed graphs, order matters. The starting place and the finishing place can be different. But here, order doesn't matter, and when we're dealing with set, we know that order doesn't matter. Okay, so that we deal with that. Okay? Okay, next. A graph is symmetric, means every time there's a point like this, there's a point like this. And we can write symmetric graphs, we saw this before, like that. Okay, so sometimes we can shorten it to that. Okay? Okay, and that's going to be related to symmetric relations. Okay, so if you have a graph like that and you take a relation of that graph, then you're going to have symmetric relations. Okay, so that's the end. There's a lot of good homework questions, and that's the end of section 3.2. Let me just tell you what section 3.3 is, what we're going to do next time. Section 3.3 is about matrices, okay? And we're going to go from matrices, we're going to go how to add, subtract, scale or multiply matrices, and then we're going to take a little break and go to section 11.3, and we're going to talk about multiplying matrices. We're going to do that all in one video next time. Anyways, I hope this was a little bit short, but it's not a hard chapter. You got to read it on your own. You got to know this stuff in the back of your fingers.